Hello, everybody. Welcome to another round of our IRIS-HEP Fellowship Talks. Today we have Shravan and Ali, both of whom were mentored by Sergey and others. Sergey, do you want to do an introduction for Shravan's work?
Yeah, sure. I'll be happy to. Hi, everybody. So Shravan, who I guess at the time was still an undergraduate student in between undergrad and graduate student. Now he's at BITS Pilani in India, and currently he's starting his graduate studies in New York University, NYU. Over the summer, he's done a very good job contributing to this and to the end-to-end deep learning project, which uses CMS open data, but is more general certainly. And the idea is to use here deep learning algorithms combined with low-level detector information. And he'll present his work, very nice work this summer, of using graph neural network representation, something a bit new also to the end-to-end project, which in the past relied mostly on other types of architecture like convolutional neural networks, etc. But this was a first foray into using graph neural networks, and you'll hear about it from Shravan.
So I'm Shravan Chaudhari, and I'm working on the project of accelerating end-to-end deep learning using graph neural networks. And as Professor Sergey mentioned, that we use E2E deep learning technique to combine deep learning algorithms with low-level detector representation of collision events to perform the tau classification. So following this idea, the goal of the project is to use graph-based deep learning approach to develop a deep learning algorithm for reconstruction of high-energy particles, especially taus. And we compare the performance with convolutional neural networks. And the second phase of the project involves integration of tau tagger, which basically performs inference for tau classification using TensorFlow C++ runtime. And this tagger is built within the E2E framework, which is based on the CMSSW framework. And finally, we developed a prototype for integration of graph neural networks with the E2E framework. So these are sample Shaw plots. These are averaged over 10,000 samples. And we have shown here Drelian tau samples, which are relatively low momentum samples, and TT bar, which is background. So we identified Drelian tau from the background. The data preparation and pre-processing step involves generation of graphs from multi-channel images. So for graph generation, we use non-zero pixels of the corresponding channel, and they form the corresponding features of the node in the graph. And here, for example, we have used k equal to 3 and in k-NN graph clustering, and we use a similar approach to define the graph edges. So, and these graphs are then fed to a graph neural network model, which is trained on Tesla P100 GPU and Intel Xeon CPUs. And here are the results which we observed. So when we see configuration of just pixel layers, we observe an ROC score of 0.697. But when we use PT tracker layer and ECAL layers, we see a significant improvement in the performance, which is about 0.856. And then as we increase the channels, as we keep on adding the channels till pixel layers and the strip detectors, we see the increase in performance accordingly. So we observed an optimal performance of about 0.887 when we include all the channels. Now, the graph neural network model was trained on the combined data set, but we have presented here the performance of identification of low momentum taus, which are Drelian taus, versus individual backgrounds, for example, WJets, QCD, and TT bar. So for WJets, it's the AUC score is about 6.3. For QCD, it's about 0.826, and for TT bar, it's about 0.942. This is a brief overview of the training data sample distribution. So from the distribution, we can see that we are more focused on the Drellian tau identification from the background, and hence we have more number of Drellian taus than Higgs taus, and the data set is balanced. And compare this GNN performance with the convolutional neural network performance, and we can see a significant difference in the performance when we just use the PT tracker layers, DZ, D0, ECal, and HCal. But when we use all the layers, including the pixel and strip detector layers, the CNN performance improves, but is still less than the GNN performance. So the second phase of the project involved integrating this end-to-end pipeline for tau reconstruction with the CMSSW framework. So the current pipeline has two data producers. The first one is event data producer, event level data producer, and the second is object level data producer. So event level data producer converts the one-dimensional low level detector arrays into 3D frames, and the object level data producers convert those three-dimensional frames into cropped frames, which are with an increased dimension, which basically corresponds to the number of objects or batch size. And finally, we have taggers to perform complex scientific analysis. So we earlier we had EG tagger, QG tagger, and top tagger, which were for electron, photon, quark, gluon, and top identification and reconstruction. Now we have added tau taggers, which uses TensorFlow C++ runtime to perform the inference for tau identification. For GNN, to integrate GNN within the CMSSW, we looked into all the available tools such as MXNet, Sonic Triton, and Onyx. But we chose to go with Onyx mainly because it's very flexible to with regards to the frameworks and tools, and it's easier to deploy machine learning algorithms which were trained on a different environment entirely on an environment which is such as CMSSW. So since PyTorch geometric is the standard choice for developing or training GNN models, we used an Onyx exporter to convert the PyTorch model to an Onyx model. However, Onyx exporter is not yet mature enough to handle all the PyTorch geometric functionalities. So there were certain restrictions in doing so. For example, it does not support KNN graph function, which is basically required to produce graphs from images. So we have to develop a module, C++ module, or a TensorFlow module from scratch to do that. And so graph producer is still work in progress. Onyx inference is what we have been able to develop. And as I said, the issue with Onyx exporter is that it does not support all the functionalities of PyTorch geometric. For example, when we use multi-sized inputs, we observe that the Onyx exporter is not able to parse the inputs correctly because of the message passing class. So it's not able to deploy graph neural network layers for different sized inputs. And a way around this is to code the GNN from scratch without using Torch geometric library, which is what we did. And we were able to deploy a small sized graph neural network within the CMSSW. It's still a work in progress since we have to scale it to a larger larger input size and larger neural network layers, a big size of the network basically. So this is just some more information on the issues of Onyx exporter regarding PyTorch geometric. We have raised issue on the PyTorch and Onyx GitHub repositories, and the issue is currently tracked internally by the Microsoft team. So you can find more information on the links provided here. And now the future goals of this project are to continue the development of the Onyx inference and implement several other architectures, especially attention-based, to see if there is any improvement in the performance. And lastly, I would like to thank IRIS-HEP for this great opportunity and my mentors, Professor Sergey Glazer and Dr. Davide D. Cross, for their help, support, and guidance throughout the duration of the project. Thank you.
Thank you, Shravan. Any questions for Shravan?
Yeah, I mean, this was a very challenging project, and I think Shravan did a fantastic job. He actually hit everything we planned to hit, and even more. You saw we had, issues raised with PyTorch and more issues identified with the current CMSSW inference system, and obviously you saw, nice improvement from the GNN. Something we thought might happen, but we weren't sure. So that was really a fantastic job, especially for someone not new to particle physics and CMS software. That was very impressive work. So yeah, congratulations. Thank you again also for the opportunity to IRIS-HEP, and I think this really made a dent in what we were doing overall.
Thank you, Shravan, and thank you, Sergey. Up next is Ali.
And so my name is Ali Hariri. I'm currently a PhD student at the EPFL and previously a master's student at the American University of Beirut. And I've been working on the project related to graph generative models for fast detector simulation in particle physics, mentored by Professor Sergey Glazer from the University of Alabama, Professor Michel Kuchera from the Davidson College, and Professor Harrison Prosper from Florida State University. And so, as you know, in particle physics, there are very complex events that have been relying on mathematical models for the simulation processes, just like we need simulations in any other multidisciplinary field. And so the LHC complex, is very complex by nature with regards to the data it's generating. And so recently there have been two main simulation frameworks that have been used to simulate the particle physics processes taking place within it. And these are parametric simulations frameworks and non-parametric ones, with the difference being that in parametric simulations, you have to specify the detector geometry and you have to account for other environmental variables, while recently there have been a surge in what we call fast simulation in order to accelerate the processes and shorten the simulation time. So in this project, we shed light on the rise of deep generative models, which have shown a great ability in learning complex probability distributions on different types of data sets, whether it's in physics or in medicine or in the other fields. And so we make use of the ability of deep generative models to learn the representations in a high dimensional space, and we apply this to particle physics. So the most widely used deep generative models are generative adversarial networks, known as GANs, and variational autoencoders. And so in this case, we make use of VAEs in order to learn the representations of particle physics data in a latent space. And so one example on the right is a deep generative model learning the features of a human face and then being able to reconstruct a novel face that has not been seen before by just correlating all the features in a high dimensional space. So variational autoencoders, as we said, they embed the data in a high dimensional space using an encoder, which could be a neural network of any type, ResNet, ConvNet, whatever. And it's the idea is that we have it as a probability distribution. We have the posterior P of Z given X, which is given as a standard Gaussian distribution characterized by some vectors mu and sigma characterizing it. And so ideally, normally VAEs are used on regular structured data like images. And there have been applications when VAEs are able to reconstruct images like MNIST dataset and other types of images for like correction and stuff and other applications. But in this case, we are dealing with particle physics data, which could be complex and irregular by shape. So we introduce like the application of a graph VAE rather than a normal VAE in particle physics. And a graph basically in this case is defined by the node feature n by c, where n is the number of nodes and c is the number of features, in addition to an adjacency matrix A, where n is the number of nodes as well. So the idea here is that graph neural networks, they transform the convolution operations from the regular image convolutions that we have seen before in AI to non-structured data in what we call the non-Euclidean space, which is basically graphs in this case. So we are able to see the interactions between the nodes of a graph in a high dimensional space. And we do that by spectral message passing or spatial message passing, depending on like the novelty of the algorithm we are dealing with. And so in this case, for the message passing, for the convolution on graphs, we pick the graph size algorithm. And the idea here is that we have a central node within the graph that is connected to neighboring nodes around it of many order of neighborhoods. So the neighbors and the neighbors of the neighbors. Now, we perform message passing by aggregating the features of the neighboring nodes over many orders of neighborhoods towards the central node. And in the process, there is like an aggregation process of the features, and that is done by either addition, subtraction, or averaging. So it's a choice. And then they are passed through an activation function and eventually sent toward the central red node, where the whole thing is concatenated with the original node feature. And therefore, we are able to obtain a whole new node representation in a high dimensional space. And so if we do that for all the nodes within the graph, we eventually get a whole new graph representation. So in this case, we want to apply the graph method for particle physics. And so our application discusses whether GNNs can learn the representations of particle jets in a high dimensional space, whether they are able to reconstruct them, and we see how fast they are able to reconstruct them as well. And so the idea here is that instead of taking jet images, we take jet graphs. So we consider that we are working on the particle hits exclusively. And so our data is basically CMS open data release, publicly accessible for all the LHC experiments. They were originally simulated using the PTS6 simulator. And yeah, we have like 30,000 samples of shade 3 by 125 by 125, where 3 refers to the number of trackers that we have, which is basically the tracker, the electromagnetic calorimeter referred to as ECAL, and the hadronic calorimeter referred to as HCAL. And so the data are pre-processed into images originally, and then we want to construct the jet graph. And so we do that by selecting the colored cells, which refer to a hit at that location. So wherever we have a colored cell, it means that we have a hit. And so the nodes of our graph are the colored cells that you see in the image on the right. And each node has associated features with it. So it's the X location of that node on the one hand, then we have the Y location of the node, and then we had the hit energy at that location. So each node within the graph has 3 features, the X location, the Y location, and the energy, and we end up having a graph of shade n by 3. And so next we have to actually connect the graph because, you know, within the graph there are edges. And so in contrast to molecular chemistry, where you have a predefined topology, in this case, we do not have such a topology. Then we use the k-nearest neighbor approach in order to just connect the nodes within each other and maximize the message passing between them. And so we iterate over many number of nearest neighbors, like 4, 8, and 16. And eventually we use this graph into an input of a graph variational autoencoder on which the graph size algorithm will operate. And finally, just like you have to pull images, then you have to pull graphs as well in this case, in order to learn a compressed and useful representation while also like reducing noise and keeping the most relevant information. And so we use the technique called min-cut pooling, where you learn a cluster assignment matrix that is a compressed representation of the original graph in latent space. And so basically, the cluster assignment matrix S is trainable, and eventually it can be used in the decoder for the depooling or like decoding. So this is our model. You have an input shape of 125 by 125, well, by 3 actually. And eventually they are split into a feature matrix X and adjacency matrix A and fed to graph size layers and min-cut pooling layers until they reach the latent space characterized by vectors mu and sigma, where we are reparametrizing them at this point and send them to the decoder. And eventually we get a reconstructed batch of a fixed number of nodes 1000 with 3 features, which are the X location, Y location, and the energy of the hit. And to train this model, we work on training the decrease of the mean square error, in addition to the KL divergence between the latent space distribution and the standard nodal distribution. So the results that we get, so we get on the top row the original reconstructions on the original jets, and on the bottom we get the reconstructed jets. And so we see that it follows a common pattern and good pattern in the reconstruction process. We have other samples attached, of course, whenever you want to inquire. And we realize that the inference time on average is around 0.1 seconds, or the runtime is about 0.1 seconds as compared to 45 seconds when we run it on the standard simulator. So we get not only good reconstruction, but we get also a speed up compared to conventional simulations. And so now we are in the phase of the generating the random samples from the latent space, and we get also fairly realistic jet images. And so the conclusion is that the graph neural network approach is feasible and successful in learning the representation of particle physics jets. And it's scalable because also we try scaling on multiple GPUs and we get a speed up. So we have the good representation, we have the scalability, and it has a good runtime as well as compared to conventional approaches. So there are still some approaches to try. So we could try different metrics like the Earth mover distance on our graphs, and we could compare this Earth mover distance, which is more specific to point cloud-like data sets, and we could compare it to the Earth mover distance to that of a regular variational autoencoder on images. And in future work, to include more realistic particle physics, we could include more tracker layers, because this is one limitation of our study. It's limited by the number of channels used for the reconstruction. So we could add more channels to it. And yeah, for now, yeah, this was the project, and I would like to thank at least my supervisors and the IRIS-HEP for giving us this opportunity throughout the summer. And yeah, I hope you enjoyed the content. Let me stop sharing this. For some reason.
Thank you. Thank you, Ali. Any questions for Ali?
I just wanted to say both this and the last one by Shravan were pretty impressive. It's a lot of really good work.
Thank you.
Any other questions or comments? All right. Thank you, Shravan. Thank you, Ali. Thank you, Sergey. Thank you all for coming.